Hello everyone and respected man. Our session is thermodynamics core concepts. Today we will explore the isothermal process, a fundamental thermodynamic transformation where the temperature remains strictly constant throughout. Over the next few slides, we will dive into the governing laws step by step, mathematical work derivation, graphical representation on PV diagrams, and key real-world engineering applications. Let's get started. So, our first term is what is an isothermal process and its mechanism. So, by definition, an isothermal process occurs when delta T equals to 0. However, maintaining constant temperature requires continuous energy balance. During expansion, heat must enter the system from a thermal reservoir to perform work. Conversely, during compression, heat is rejected into a sink because the internal energy is unchanged. All absorbed heat converted directly into work. Governing laws and equations. Because temperature is fixed, ideal gas behavior follows Boyle's law. Pressure is inversely proportional to volume. As a gas expands, its pressure drops proportionally to P1 V1 equal to P2 V2. From the ideal gas equation, PV is equal to nRT. Since N, R, and T are constant, the product of pressure and volume remains strictly invariant across any state. Pressure volume diagram. On PV indicator diagram, an isothermal transformation plots as a smooth hyperbolic curve called as isotherm. Higher curves represent higher absolute temperature. The total area underneath is isothermal between V1 and V2, represent work done. Change in internal energy delta U. For an ideal gas, internal energy is solely a function of absolute temperature. Since temperature does not change during an isothermal transformation, the net change in internal energy delta U is strictly 0 joules. Applying first law of thermodynamics, delta Q is equal to delta U plus W, we find that delta U drops our entire essential processes conditions. For an isothermal process to occur ideally, three conditions are necessary. First, perfectly conducting container walls and pistons to allow instantaneous heat transfer. Second, quasi-static execution. The process must happen infinitely slowly to thermal equilibrium, is maintained at every instant. Third, contact with an infinite heat reservoir capable of supplying absorbing heat without changing its own temperature. Work done. Work done is equal to nRT ln V2 upon V1 while preserving stability. Adiabatic process it lower work due to temperature drops, and isochoric process produce zero work because volume remains fixed. Real world applications are where do we see isothermal process in the real world? Natural phase transitions like ice melting or water boiling at constant atmospheric pressure absorb latent heat isothermally. So now we will see isothermal versus adiabatic comparison. Let's construct the isothermal adiabatic processes. In isothermal system, temperature is constant, heat exchanges freely, del Q is equal to W, and walls are perfectly conducting, following PV is equal to C. In an adiabatic process, heat exchange is zero. Temperature varies, internal energy drops, do work delta is equal to minus W. Work done derivation timeline. Finally, let's dive into isothermal work formula. We begin the work with integral W is equal to P delta V. Using the ideal gas law, we substitute pressure and nRT upon V. Since nR and T are constant, we factor them out. W is equal to nRT integration 1 upon V dV. Integrating from V1 to V2 gives our final equation. Work done is equal to nRT ln V2 upon V1. Thank you.